Welcome to Zero Knowledge, a podcast where we talk about the latest in zero-knowledge research and the decentralized web. The show is hosted by me, Anna.
And me, Frederick.
Before we start in on this week's episode, I want to tell you about the ZK Summit. The ZK Summit is a biannual event focused on zero-knowledge research, optimization, implementation, ZK use cases, universal trusted setups, no trusted setups, recursive snarks, cryptographic primitives, privacy, and math. This will be the 5th edition. It's put on by this podcast, the Zero Knowledge Podcast. It's happening on March 31st, and it's an online event. Attendees will be primarily researchers, cryptographers, practitioners, and founders working on zero-knowledge research. In the past, it's been an awesome event. I can't wait to see what it's like online. So if you're interested, find the link in the show notes or look for the ZK Summit on Crowdcast. For those of you who already applied for the event, you should check your inbox. You should have received actually an invitation to this. Just the date again, it's happening on March 31st, 2020. Event starts at 7 a.m. PST, 10 a.m. EST, and 4 p.m. CET. So hope to see you there. And now here's our interview with Benjamin Perez from Trail of Bits. So today we have Ben Perez from Trail of Bits. Welcome to the show, Ben.
Hey, thanks for having me.
And we also have Frederick.
Hello.
So you may be familiar with Trail of Bits as they are sometimes sponsors of this podcast. This episode is not sponsored by Trail of Bits. In fact, we've had JP on in the past. JP is a colleague of Ben's who also is an auditor at Trail of Bits. But when we had JP on, this was like peak 2017, 2018, crazy ICO time. And in that interview, we actually got a chance to cover like what the role of an auditor was, what the company was up to. And it's been a long time since then. And I think what I want to do with part of this episode, at least, is try to understand better how the role of the auditor has evolved in the space, because it is no longer 2017, 2018 with the ICO boom. So what has changed? So maybe we can start there, Ben. Oh, actually, before we start there, why don't we learn a little bit about you? Ben, what's your background? How did you get into this?
Sure. So originally I was just like a math person who is like loosely interested in cryptography. I started doing a PhD in like post-quantum crypto, and that was at UC San Diego, but eventually left for industry, for Trail of Bits specifically, because I wanted to be working on projects that were a bit more applied. And like, of course, I have a soft spot for the theoretical research that academics work on, but I really like building stuff that gets actually like deployed. So that's kind of how I got to Trail of Bits.
When did you actually join?
I joined in like April 2018.
Okay. So would you say when you joined, was it still like very ICO focused?
It was. So it was actually kind of like a culture shock for me, because before coming to Trail of Bits, I didn't have a lot of experience in blockchain.
Okay.
I came from the crypto side. So when I started, we were getting all these like, whatever coins and just like totally like wrecking them, finding all these bugs. Actually, one of our tools kind of came from the fact that we were just able to like print free money in a bunch of these altcoins. And we were like, well, I think we can automatically just detect this and, find this stuff within like 30 minutes. So we did. And that was like a lot of those early mistakes in that space kind of led the development of our tools. So.
Interesting.
Yeah, I think that's interesting. I mean, we talked to JP about some of these things too, and like some of the things that were evolving at the time. And I think Trail of Bits has been on the forefront of a lot of this stuff. But even from the point that you joined to now, how do you see that changing? Like, is it still, like, I have to imagine that it's less crazy, get rich quick scheme stuff and more, the companies who actually raised money, who actually are building something now.
Yeah, I think that's exactly right. So, back when I started, like I said, we were just like kind of doing these like really short, quick audits for random ICOs. Not random, these were like legit companies. We didn't do any scams, but like, now I think what we see is we still get just as much blockchain work as we did back during the ICO mania. But these are companies that are like really at the cutting edge of new research in the areas of like proof of stake, zero knowledge stuff, other like really advanced cryptographic research. So I think it's actually gotten a lot more interesting. These companies are like amazing to work with, and in some sense have like more challenging problems that they're working on.
Has the type of work changed much from smart contracts to like underlying tech? I mean, I know we use at Parity, we use Trailbits to audit our stuff every once in a while, and we never do smart contracts. It's more like auditing clients or auditing like core libraries. Has that type of work changed, or is it still a lot on the smart contract side?
I think that we've seen a slight decrease in the amount of smart contracts that we see. We still do get a lot, for sure. So like the tools that we built out to do that still have like a lot of use. But a lot of the companies that we're seeing now are building out these new blockchain protocols in like Rust or Go. And so we've actually now started to build up tooling for auditing Rust and Go code bases. And also because a lot of these companies are doing stuff that's like really novel with cryptography, a key part of the audit these days is actually kind of looking at the papers that these people write and making sure that like it actually checks out from a cryptographic perspective. So I would say it's less, kind of analyzing this like, well, when you're on the blockchain, it's a very confined environment. You know, it's all Solidity running on the EVM. But in these cases, there's sort of like a lot more that can happen. So I'd say that these audits can be like a bit more dynamic.
I mean, there's basically no white paper or like blockchain white paper that I've ever read that actually proves what they claim in the paper. I imagine auditing that has to be, I mean, both interesting, but also hard to like actually say, no, this holds.
Yeah, I mean, there are different degrees of it, of course. So like some people kind of come in with their like, you know, hey, we rolled our own like verifiable random function or whatever. And, you know, like, here's what we think works, like kind of good luck, you know, auditing it. Those are actually sometimes the most fun. But, you know, there are a lot of people in this space that are being really cautious that hire like, you know, PhDs in cryptography. Those folks tend to point to papers that have seen some amount of peer review. I think in the history of cryptography, we've never seen such a quick turnaround time from academic publication to deployment. And there are a lot of subtleties that don't really like manifest themselves in the paper. So there might be a security proof, but there also might not be a part of the paper that says, oh, by the way, here are all the edge cases that you need to check in code. And if you fail to check those, any of them, someone all of a sudden can forge signatures or whatever. So there's just like a lot larger of an attack surface.
I bet. Do you think like the character, going back to that, you know, that earlier episode that we did where we talked about the character of the auditor, do you think that the makeup of the team has changed? Are the people that are actually capable of doing these kinds of audits different than the people who would have been maybe focused more on those early quick ones?
I think we still need, I think that there are more types of people required now to kind of do a comprehensive review of these systems. But it's not like the people who were doing the early blockchain audits are like now all of a sudden like had like dated themselves. You know what I mean? Like I still do see a lot of audits where we need to do like smart contract audits. But also I think that the kind of person who's good at just like poking around a code base and like figuring out the ways that it breaks, you know, even if what you're doing is very advanced cryptographically, you know, maybe 70% of the bugs are still just going to be someone implemented some logic bug in code that doesn't have anything to do with the cryptography. And we'll actually talk hopefully about that later with some of these new attacks from Dan Bonet and Zcash. But there's still a huge attack surface at just like the like app development level.
Got it. So I know that, I mean, Trailbits has created a few tools to actually like catch these bugs, but were those tools originally more for like Solidity code? Like, do you have to change these tools to actually work on different types of programming languages?
Yeah. So some of our code is very Solidity specific, or some of our tools are very Solidity specific. So the three main ones, just to like kind of go over it, is like Slither, which is a static analyzer that can like just look at the Solidity source code and find common bugs. So that's very Solidity specific because it finds like anti-patterns in writing Solidity code and kind of like warns you about them. Then Echidna is a fuzzer. So there are fuzzers for like a wide variety of systems, but basically the idea is the same for all of them, which is just like you start calling the functions that are publicly exposed in the code base with sort of intelligently picked random values. And then you hope that at some point you force something to crash. So we have fuzzers for a lot of different things, but Echidna is the fuzzer built specifically for EVM.
I see.
The most dynamic tool that we have, though, is Manticore, which is the symbolic execution tool that we have. That has support for a wide variety of systems, one of which is EVM. So that is a bit more flexible, and we can use it in audits that aren't strictly within the Ethereum ecosystem.
You also have a bunch of other stuff like Binary Ninja. There's a bunch of other stuff that deals with both assembly, and I think we touched on this with JP as well, being able to lift code into LLVM IR and then doing analysis on that. All of this stuff. So the reason I mentioned the LLVM thing particularly is because it suddenly allows analyzing Rust code, WebAssembly code, a bunch of other things, because these are all things that go through LLVM in some way.
Totally. Yeah. So a huge part of what TrailofBits does so I think that we're really known for these like audits that we do, but there actually is like this whole other side of our business, which is government funded research. And that's where we get money to like build binary analysis tools, binary translators, even like symbolic execution tools like Manticore. That was originally a government funded project. We have quite a bit of tooling around that. And actually, what we're going to be doing with Zero Knowledge for DARPA coming up, that's going to use a lot of our binary lifting tools as well. So, we can talk about that more in a little bit.
Cool. And so my last question about TrailofBits specific, before we go into the ZK stuff, is about the question comes because I had a conversation with Dan, the CEO of TrailofBits, Dan Guido, I think a year ago maybe, where we talked about this idea of doing simulation work, like actually trying to model things past just the code, especially in cases of like POS systems, like actually explore what the outcomes of the economic models could be. And I wonder if that's something that you guys do or did or plan on doing?
Yeah. So this comes up in some audits that we do where we talk about economic incentives with the people that we're working with. So obviously you need cryptographic security in your blockchain and all that stuff. But you also need to incentivize miners and all of the people involved to do the things that you want them to do. And I think that in some cases, especially with these proof of stake systems, you run this risk, if you're not careful, of being able to have the folks making decisions about your network susceptible to basically bribery or sort of buyouts. Mm-hmm. And there's actually a really good paper on this from Phil Diane and some of the folks over at Cornell about dark DAOs. And it's this notion that you can temporarily sort of lease your key to this decentralized network of malicious actors that will pay you to use your vote to kind of launch attacks against the network. And so, this stuff gets really complicated, and it is sort of this interesting intersection between cryptography and economics. And actually, we offer jointly with another organization economic and cryptographic audits of blockchain projects.
Oh, interesting.
So that's some very exciting work that we're doing.
Yeah, to me, that actually goes outside of the role of what you think of it when you think of a tech auditor. It's almost like consulting. Then you're giving some further analysis there past the actual code.
Yeah, it is a bit more outside the scope of what we would normally consider an audit. Fortunately, in these cases, it's sort of within reach to sort of mathematically model what people do. This is a less like open world system than like, the US economy or whatever.
Yeah.
So it's easier to kind of sit down and be like, okay, how are people getting paid in the system? How does that payment incentivize the right behavior and all that stuff?
Yeah.
So
I think, this is something that we're seeing, a huge influx of these incentivized test nets. It's basically only to try to test the crypto economics. And the problem with them is obviously that you're not going to get the same kind of engagement and behavior as in a real network with billions of dollars at stake if you just have, you get $50 if you win this thing. So it's a weird situation. And I think like Tarun, who we've had on this show, him and his company basically exists just to try to build these models and simulate things and try to build tools to see if we can test crypto economics. But it's actually seems like a really hard problem.
Yeah, I think that you can kind of do some back of the envelope, calculations to see what the incentives here look like, but actually like running a simulation of that system, that's a substantial undertaking. And requires a lot of expertise in, distributed systems, cryptography, economics, on top of having, like the tech stack to do it. So, yeah.
Who do you partner with to do this?
Yeah, so the service is called Mainnet 360. And that's, this joint economic and security that we do with the Prism group. They're, a group of economists who do some really great blockchain work and can help us sort of fill in our gaps where we don't necessarily know economics at a deep level. We're computer security people. So, that partnership's really exciting, and I'm excited to see where it goes.
All right. Next up, let's move towards the ZK stuff. I want to hear a little bit more about how first of all, I want to understand, why is Trail of Bits interested in zero knowledge research? Everything we're talking about looks more like code audits and Solidity and EVM and even modeling. None of those things are necessarily zero knowledge. So where does that interest really come from?
Yeah, so I think the Trail of Bits is kind of unique amongst organizations that do these sorts of things, because we have a lot of people who were formerly academics. I myself, like I said, started a PhD and decided to leave for industry. And as a result, I still have this like soft spot for really cool research problems in cryptography. And so personally, I like to do audits and work in general that involves what's exciting in cryptography right now. And in my opinion, that's these privacy preserving tools like zero knowledge, multi-party computation, things like that.
Mm-hmm.
So yeah, I think the push comes from within, but also just that like the good blockchain work right now is taking these privacy concerns seriously.
Would you say that so in this case, are you saying that sort of the auditors or like some of the staff got very excited about this and started to like pressure management to like find these projects? Or do you feel like the projects emerged for you?
I think that we built up a reputation for being, good with blockchain from the ICO mania, which is, when you talk to JP. And then that kind of put us in this good position to audit this second wave of blockchains, which is a bit more, cryptographically oriented. And that combined with the fact that we have this great crypto team with a lot of expertise in zero knowledge and multi-party computation, kind of like it just made sense to start looking for those types of projects.
So what are those projects? Like what does an auditor do with a zero knowledge proof system? In academia, you have, people creating some of these systems, and then you have other either implementers or other academics analyzing them and looking at through the math. But is that like, I guess the question here is like, does that need an audit in the traditional sense? Or is that more like you guys are kind of stepping outside of the realm of being an auditor here and starting to like participate in this research? I'm just trying to figure out if that's like actually the same job.
Yeah. So I think that, what an auditor is flexible. We do what it takes to make sure that the companies that we're working with are as secure as possible. So when I see a system that uses stuff that's really cutting edge like this, I usually spend a lot of time, like I mentioned earlier, reading the papers, making sure that the code actually adheres to what they said they were doing in the paper, and kind of finding all of the holes and edge cases that they hadn't necessarily thought of. I think the transition from something that you write as like a theoretical cryptographic construction to a thing that exists in the real world and runs on real hardware, that gap is huge. And so while we don't necessarily find like a groundbreaking bug in a core zero knowledge protocol that is, has a security proof or whatever, those are rare. But a lot gets mixed up in that transition to code. And I think that that's where we really shine. Because we understand these papers and we understand the ways that they might break when they're actually being deployed.
Yeah, there's like a lot of different layers here, right? Where, compared to what we talked about, white papers, like these are not white papers, they're actual papers. And to right. be an actual paper, you also need to include proofs. So I guess like you're at least coming from the luxury of having a system that's peer-reviewed and to some degree proven on paper. But then sometimes the paper writer, like most recently, like it seems like most of the paper writers are actually implementing this thing as well. So you have the implementation of the paper, usually from the same authors, and then you have a user of that implementation. And things can go wrong at each of these stages, right? The paper might be wrong, the implementation of the paper might be wrong, the usage of the library might be wrong, or like complete misunderstandings about what the security, guarantees actually are. In what level do you work mostly? Is it on that last step, or have you worked even with some of the authors of these libraries to audit the libraries themselves?
We've certainly worked with people who are putting out cryptographic research papers and are writing core libraries. Those are more challenging audits for us because those people are like really smart, but we do find bugs, and people, again, they forget to check edge cases. And these systems are they're so complex. They rely on so many different primitives. If you're doing zero knowledge, you need your like commitment scheme to work. You need the circuit compiler to work. You need to do pairings on elliptic curves. Any one of these subsystems failing is going to like totally sink you. And so there's just a lot of space there for finding bugs. But I also think that a big concern that I see in this space is we've kind of moved past the phase where only, a couple hundred academics understand how zero knowledge proofs work. This has gotten a lot of hype, and now new projects are going, hey, like, why don't we roll out a ZK snark or some form of zero knowledge proof? And those people are maybe not as cautious as the people who are writing these papers because they're not as familiar with the ways that crypto can go wrong.
This is something that I see a ton happening where it's really interesting with this podcast and like being out there in the world talking to crypto projects. Like when I talk to people who want to use this stuff, they're just like, oh, this new thing came out, we're going to use that instead. And they start integrating it. And I'm just like, holy fuck, are you crazy?
Yeah.
And then when I talk to the author, it's like, oh yeah, we'll see where this goes in the next 5 to 10 years. It's like
exactly.
completely different expectation levels.
And I think that, of course, it's all about striking a balance, right? On the one hand, crypto research doesn't do anyone good if it sits on the shelf forever. But rushing out to deploy one of the like 10 ZK papers that came out in 2019, that's a risky thing as well. And I think, this isn't just a problem with zero knowledge stuff. I've seen a lot of hype around these verifiable delay functions recently, which again, like really cool stuff and really legit people are working on this. But all of a sudden now, your blockchain might rely on some cryptographic assumption that is relatively new. And we just don't know how robust that is. And I think that the good people in this space are, expert cryptographers, but they also understand what they're going to do if something goes wrong in one of these protocols. So like Zcash is a great example of people handling this like absolutely the right way. There was a bug in that paper that let people forge Zcash, and they were able to fix it. Like they just handled that vulnerability disclosure exactly how you'd want. And stuff like that's always going to happen. You're always going to have bugs in your code. And I think that what I want to see is that, people deploying this really like new, somewhat risky stuff, they have a plan and they're going to handle this like the right way.
Yeah, we did an entire episode on that with Sean Bowe that we'll stick in the show notes. This is like from last year. That was the vulnerability that was found in kind of the original implementation, the libp2p. This was actually from paper to the first academic implementation, incorporated into a project, and then it was found that there was something in that first implementation that had been sort of overlooked, and that caused this vulnerability to emerge.
Yeah, exactly. I mean, and this is the sort of bug. I mean, so when Trail of Bits writes up a report, we have the severity of the bug and the difficulty to exploit the bug, right? So, you might have like a really like critical vulnerability that also requires someone to be like extremely advanced to exploit it. And bugs like the one in Zcash is like one of those things where there are like 100 people in the world that could have ever found that bug.
And like 12 of them worked on that project or something like that.
Exactly. So like it was handled exactly the right way. But so the things that I worry about more are like what happened with the Swiss voting system. So this is a voting app that used zero knowledge proofs in several steps of the process to demonstrate that the voting authority wasn't either adding malicious votes or falsely like decrypting votes to things that they weren't originally. And these folks used a system that sounds right in theory, but in practice, they were having problems implementing these cryptographic primitives like commitment schemes and then doing the sorts of things that you need to make the proofs non-interactive. And this kind of demonstrates like the people at a high level understand what they should be using. They know which libraries to pull from, but then when they actually like have to roll it out, they don't have an intricate enough understanding of the system to get it right. And so that's what I'm worried about with this new generation of blockchain projects rushing to roll out this research.
What was that Swiss voting example? We've heard that before, but do you remember what it was?
Yeah, so that was the voting software built by Seidel, and the team of researchers that found these bugs were that was led by Sarah Jamie Lewis. Yeah, that's the stuff that really keeps me up with these zero knowledge systems is people who like half know what they're doing, trying to roll it out and just getting these like subtle details wrong.
I mean, that brings me to a question of how do you audit a system like this? Because, if customer comes to you and says, okay, here's 500,000 lines of code for a voting system, please make sure that it's secure. What's the process? How do you just not say, oh yeah, that's going to cost you $10 million?
Also, because like, I can't imagine that the tools that you have right now are necessarily like tuned for this kind of audit.
Yeah. So I think we really take like a multifaceted approach here. So we split the team up based on what the concerns of the folks that we're working with are. So usually we have someone who's just like an AppSec person and can like wreck whatever code you throw at them. Like they're just going to find like gnarly like Rust and Go bugs that don't really have anything to do with the higher level system specification. So they work on that, and then usually, especially if there's crypto involved, we have someone like me or one of our more academically oriented folks working on kind of like analyzing the crypto spec and the paper and sort of triaging that with what's actually written in code. And then for a system that that is complicated as a voting system, we'd probably also have someone doing like an architecture and threat model review. So of course, like, if you hand us 1 million lines of code, we're not going to like actually look at all 1 million lines of code. But I think that part of the skill of being an auditor is being able to like hone in like really quickly on the pieces that are going to be relevant to you. And we actually have some tools that help us do that. So with Rust, we have this tool called Manero file, which helps you find risky places in Rust code bases. So, in Rust, there's like all these nice like type level protections that make sure you can't shoot yourself in the foot in certain ways. But you can sort of override that. You can say like, oh, I'm smarter than the compiler or whatever, and like, trust me, I'm doing the right thing. So you can insert unsafe code into Rust. But when you're writing code that calls a ton of other libraries, it's not always clear where those unsafe calls are happening. And so Siderophile helps you drill down into like all of the like dependencies and places that you're calling that you might not necessarily even like realize that you're calling, and help you find the right places in your code to audit. So we can use stuff like that as like a guide to help us focus ourselves for like a shorter audit with like a huge code base.
That's cool.
I've sort of been curious about this. Like, is Trail of Bits focused on building an army of auditors, or is it focused on building tools so you don't need an army of auditors? I feel like it lives between those things.
Yeah, I think I'd like to think of us as more of a bunch of like specialized like precision knives than an army. You know what I mean? Like, I think we're all about coming up with like tools that can automate the things that are sort of time consuming, but not necessarily like intellectually challenging for people to find. So like with like Echidna is a great example of this, or fuzzers in general. They help you kind of figure out the little places where things might go wrong so that you don't waste time combing through the entire code base to find that, because a machine can do that for you. But once you actually get there, it requires a lot of expert knowledge to actually figure out what went wrong and then figure out how to fix it. And especially with the crypto stuff, there aren't really good tools for going, hey, you like chained together a bunch of cryptographic primitives together in like the wrong way. And now all of a sudden there's like a padding oracle here. And if someone, had like query access to that, they could like get your secret key. Like, that's just like not a thing that's like automatable right now. So I think we want to get people looking at the problems that people can solve, and tools looking at the problems that are automatically detectable.
Let's keep talking about some of the other vulnerabilities that have come out. You mentioned actually just earlier in this episode, this Zcash and Manero vulnerability, I believe. There was in both systems, and it was these side channel attacks.
So I'll just talk about the Zcash case, because it's a little bit easier to understand, I think. And basically the idea is, okay, so in Zcash, let's talk about like the life cycle of a Zcash transaction. So a user creates some transaction that they want to send out to like the shielded pool. So of course in Zcash you have transparent transactions, which like anyone can see and just as like Bitcoin. And then you have shielded transactions, which are anonymous. And so a user creates a transaction that they want to send out into the shielded pool. And then they prove that this like commitment of their transaction does all the things that Zcash says that a transaction should do. And then they send that out to the peer-to-peer network, and it kind of distributes itself amongst all the nodes. And then each node takes that transaction and it checks to make sure that it's valid. And because of the nature of private transactions in Zcash, the only way for you to know that you've received a transaction is to actually try to decrypt every single transaction that you see. There's a little note field on every transaction that if you are the recipient, you can decrypt, and that allows you to spend the ZEC contained in the transaction. Okay, so like that's like this basic setup, but what Dan Bonet and a few other people found is that there are some side channels here. So like the actual ZK snark itself isn't vulnerable. Like that works as expected. But here, this is like exactly the kind of bug that Trail of Bits looks for in audits, is like the way that was being used at a higher level in the protocol opened it up for these weird attacks that allowed people to de-anonymize users. So the first one was called the ping attack. And the ping attack basically takes advantage of the fact that your wallet, which is like what has all your keys and lets you sign and spend transactions, and the node, which is the part that kind of maintains the current blockchain state and is like validating blocks and transactions, those two entities run in the same process on your computer. So they're not like two different apps. They're like the same thing. So what happens is when a node receives a transaction, if that transaction actually belongs to you, the wallet, that transaction will take longer to process. And that's because you've successfully decrypted the note, and then you check to make sure that a bunch of other things are like working the right way. And so the attack here is, okay, so if I want to de-anonymize a user and I see a node receive a transaction, and I want to see if that transaction belongs to the person who runs that node, then what I do is I immediately follow it with a ping message. And a ping message here is not like a Zcash specific thing. That's just like a networking thing. And the node will respond like, hey, I got your ping, whatever, when it actually like processes it. So if the transaction doesn't belong to the person who received the ping, that'll take shorter than if it actually did belong to the person who receives the ping. And that's because, again, these two things are running in the same process when they really shouldn't be. So you can think of it as like the ping comes in and has to wait in line behind the transaction. And if the transaction doesn't belong to the wallet, it'll, not do all these checks and just kind of zoom out more quickly than if it did, it'll get stuck. And so the ping will take like milliseconds longer.
And that's the tell, I guess.
Exactly. It's so if you can time this stuff, you can actually de-anonymize people in the Zcash network. There's another attack called reject, and it's a little bit weaker than ping. It's basically like, maybe online I have some service that I'm running that you can pay in Zcash or Zec. And I give the address, but I want to remain anonymous. I just want to like get this money and like cash it out or whatever for like the service that I'm offering. You could go, okay, I want to actually figure out which node corresponds to that address, because then I can like go, well, if I know the node, I might be able to figure out the IP address and then actually find out what like real person runs that service. So then what you do is you pay the address that you wanted to, but you actually encode the transaction in a way that it's going to fail. It's going to like fail at the parsing level. And so you send them the transaction, and they're their wallet receives it, and they're going to start trying to decrypt it. And then all of a sudden they're going to go, wait a second, this is like a bogus message. And instead of just like silently failing, they're actually, that error trickles up to the node layer, not the wallet layer. And then the node sends back this like reject message. And so then that they actually were able to decrypt your thing and made it to the part where they have to like fail, or where they're parsing it. And you can, get their IP address and all that stuff. So.
And this vulnerability that you described, it was discovered by Dan Bonnet, and who else was on that?
Dan Bonnet, Florian Traumer, and actually Kenny Patterson. Yeah, two folks at Stanford, and then Kenny's at Zurich.
But in this case, this discovery, this came from academia, which is kind of what, like, this is just interesting, because then you see like there's also academic zero knowledge proof teams that are also doing sort of that bug discovery. This is not like what I'm so used to seeing are the papers where they release like, this is, the new protocol, this is our new idea, here are the proofs for it. But this is actually an attack discovery. So like, do you see there's like being a combination between like industry folks like yourselves and the academics actually doing the same job?
Yeah, well, I think that now more than ever, we're actually all kind of in the same boat. So like Dan Bonnet, I mean, he's obviously this like incredible theoretical cryptographer, but he's an advisor to a lot of these companies. And like Matt Green, also great theoretical cryptographer, but also a founding member of Zcash. And so now there's this incentive for these academics to work on problems that before, like, some random attack on some random cryptocurrency isn't necessarily a great conference publication, but now all of a sudden it's really valuable. And so I'm glad to see that incentive structure has sort of shifted from what is like theoretically interesting and will get you a spot at crypto, the conference, which is very academic, to, hey, let's work on real problems that affect like money held by real people.
Yeah. Although I don't know if is Dan connected to Zcash? I actually don't know that he is, but
yeah, I'm not sure.
I don't think so.
I know. I think he's attached to some cryptocurrency company, but I couldn't tell you which one. Yeah, and there's also been a lot of cool stuff kind of looking at. So speaking of issues that where the zero knowledge protocol itself is doing the right thing, but higher above it on the stack, things are failing. There's also all this like traffic analysis stuff in Zcash. And I think that's really interesting and kind of like plays well with this ping reject attack. So like obviously there are a lot of users of Zcash and you can't like try to de-anonymize all of them. You want to actually have like a target. And I think that this traffic analysis stuff helps you pick that. So like basically the idea is well, very few Zcash transactions are actually private. I think that's a thing that maybe we don't talk about enough, but like it's like 1 in 10 Zcash transactions are actually shielded. So that puts you in this like sort of like Tor situation where because not that many people use it, when someone does use it, it's like, whoa, something's going on here. And the folks that wrote this paper basically were like, even amongst the transactions that are private, like 85% of them or something like that are just from block mining, because the Zcash protocol says that all ZEK mined in a block has to go to the shielded pool before it can go out and do things in like the outside world. And so if you analyze that traffic, you can basically deduce that like 85%, and remember this is only 10% of the total Zcash transactions that happen, like 85% of those are just people mining money and immediately pulling them out. And so then you're left with this like really small number of transactions that are like legitimate, like shielded transactions. And once you get there, you can start doing stuff like this ping reject stuff where you're like, oh, well, who's getting this thing? Who's getting this thing? And it sort of all just like coalesces together to make the network less private than you'd think. Of course, Zcash did fix the ping reject attack, but this is the sort of stuff that I worry about with ZK.
I think a lot of this type of research, I mean, I also feel like it happens a lot from the academic side. I don't know if it's a recent thing, or I've kind of seen it as always happening to some degree, because a lot of people trying to get PhDs and they have to be doing something. So they analyze systems that exist. And, you know, if you just look at Stanford Blockchain Conference, there's a ton of academic stuff there talking about Bitcoin, talking about all these deployed systems, just looking at their security properties. And I know Ethereum, like all the Ethereum clients have gotten multiple reports from various universities saying like, oh, here's a network discoverability thing, network analysis is super common. But the serious ones are things like, here's an Eclipse attack. If you manage to do this complicated thing, then you can potentially like single someone out and make sure that they're not getting any transactions or censor them in some way. And there's, I feel like that happens a lot, but yeah.
Yeah, and I think that this is a good thing because, well, I mean, like I mentioned before, obviously we want academics to work on problems that affect industry, but also like for new grad students, having it not be the case that like your first problem is some daunting theoretical piece of research and is like, hey, why don't you just try and break the security properties of like Zcash for a while? Like that's a more tractable problem in some level than like invent a new zero knowledge system that is like faster than all the previous ones. Like that's like a really scary thing to work on as a PhD student. So,
the best way to learn something and understand something is trying to break it.
Of course.
Going back to that question of like, why does Trail of Bits care about zero knowledge proofs? Are you actually working on any particular projects that involve zero knowledge research today?
Yeah. So we just were awarded a grant from DARPA to do a bunch of zero knowledge work in this area of like trying to prove that you have an exploit in zero knowledge. The program, which is called Civ, is much more broad than that. It has a lot of different people trying to find different real world applications of zero knowledge proofs beyond blockchain. And then sort of a bunch of academics trying to actually improve the speed of these systems. But the problem that we're focused on is I have an exploit and I don't want to tell you how that exploit works, but I want to prove to you that it's legit.
Hmm.
And that brings up a whole host of new problems that I think have not really been tackled by the zero knowledge community. So just sort of like stepping back a second, most zero knowledge proof systems require you to represent the problem that you're trying to prove as a circuit. And it's not just like a circuit like with like wires and stuff. This is like basically a graph where each node is either an XOR gate or an AND gate. And so these are like really like bare bones logical operations. So what we need to do is convert the notion of being able to exploit a piece of software to this like really like low level notion of a circuit. And that really actually like plays into a lot of the things that Trail of Bits is good at. So the way that you do this is you actually build up a model at the circuit level of how a processor works. So some folks did this before with a thing called TinyRAM, which is like a toy little. So like stepping back a second, your computer like uses a processor, and that chip has like a language that it speaks. So that's called like, it's like assembly language. And the one in like your MacBook Pro or whatever is like super complicated, right? Like it's this like advanced piece of technology that we've like spent forever building, and modeling that is like really daunting. But you could model maybe a chip from like the 80s, and those are like really simple. So these researchers built a model of this, and what you could do then is,
and this is TinyRAM.
This is TinyRAM.
Yeah.
And you can use TinyRAM to prove in zero knowledge that you executed some program correctly. So you can say like, we both agree on a program and the hardware that's going to run on, and I'm going to prove to you that I have some secret input that causes the program to end in some state. I mean, that's like basically exactly what you want to do for a vulnerability. You want to say like, hey, I have some input that's going to like crash the program or let me like hijack how your computer's actually like executing the program. But the problem with the previous research is that TinyRAM is not a real machine, right? A lot of exploits that you see in the wild where people are like all of a sudden like able to like execute any code that they want on your computer, like get all of your data, like these really, really bad bugs. Those actually rely on the subtleties of the chip that you're using and the operating system that you're using. And so what Trail of Bits wants to do is go, okay, like people modeled these toy processors before, but we're going to model the real deal. And we're going to bring all the tools that we've developed, like these binary lifters, binary translators and stuff, to create models that are efficient for zero knowledge proof systems.
And I like, so that idea that the actual project that you work on is this idea of the ability to disclose or to prove a vulnerability in code without disclosing what it is or where it is or something like this.
Yeah.
And I mean, the applications of that would be awesome. Like the idea that you could break a system, prove to a company that you've broken the system without revealing what that is. And I guess then you could actually like get them to pay you or something.
Yeah. So I mean, like,
although that could also be used really maliciously, because then you could say, hey, I broke your system. You don't know how I broke your system, and you better pay me or I'm going to break your system.
Yeah. I mean, I think that, so, you know, like the dream application of this is like, you know, we have these bug bounty programs, but you could have like a decentralized bug bounty with this. You could have like a program that's funded maybe on the blockchain or something like that. And then if I can post a valid zero knowledge proof that I can exploit the software that you have a bounty for, I get paid out. And then there's no like trust there. I don't have to like be like, oh, I promise I have the bug, but you got to give me the money first, or like, oh, I'll give you the bug first. Like there's this whole like weird back and forth. But then there's even, I think, a more broad use case that I think kind of gets into like consumer protection, which is like, there are a lot of companies that don't have bug bounties, and they actually don't want to seriously address vulnerabilities that researchers discover in their code. And this is kind of a way of protecting consumers by being able to post a zero knowledge proof that you have an exploit and saying, hey, I'm not going to tell people how to break this because the company's not going to fix it. Or it might not even be fixable. Some companies hard code their software into like an IoT device. But that way users can know like, hey, this thing that I'm about to buy, this like smart fridge or whatever, has a lot of zero knowledge proofs of exploits on like whatever website. And maybe that's not the smartest thing to buy. But the people that already have them aren't put at risk by this like bug disclosure.
I think we actually, in our conversation with Isaac Meckler from O1 Labs a few weeks ago, we talked about this like zero knowledge proof for compliance or zero knowledge proof for verification. And I remember he had an example sort of along the lines of this, where you would be able to prove that a certain kind of code was used in something without disclosing what that code was. But here it's more, things are broken. I can prove that they're broken, but I won't endanger those that have this on their computer. But I will give people an option to make a better decision. This is super interesting.
Right. Or, you know, if the companies decide to fix it, you could actually then rerun the zero knowledge proof to show that the exploit can't happen. So you could have like a zero knowledge proof that the exploit exists. And then if they fix it, a zero knowledge proof that they fixed it. So like, that to me is really exciting, and hopefully kind of like can improve what I think is like the not so great state of vulnerability disclosure and protecting people from, you know, bugs in software.
The DARPA project is bigger than just what Trail of Bits is working on.
It is.
Are there like resources we can find on this? Like, is there some documentation anywhere?
Not yet.
Okay.
Right now, like I know who else is on the project and I kind of know what they're doing, but I can't say because they haven't like announced it.
Got it.
How about we round out on the topic of ZK? What do you see as the future for this? What will your future involvement be in this? Curious to hear your opinions.
Yeah, so I think that, like I've been saying, I think that there are a lot of people in this space who, you know, are total like experts at ZK, and they're building systems that like work great and they understand how to fix them when things go wrong. But we're seeing people who are not like expert cryptographers trying to use this technology, and that's what we want, right? We want people to use ZK and to get the privacy guarantees that it provides. So I think that where we need to go, you know, on top of like improving all the efficiency and that stuff, is really building libraries that are usable for people who don't know much about zero knowledge, so that people like voting companies, like blockchain companies that aren't, you know, staffed with a bunch of like Stanford PhDs, so that they can use this stuff too. And I think that this is sort of like a broader emphasis that I'd like to see cryptographic engineers kind of like focus on, which is, building libraries for people who aren't experts. And I think that that gets into some stuff that we aren't necessarily good at intrinsically as math people. Like, we need to build APIs that are misuse resistant, and we need to think about users in a way that we haven't necessarily thought about before. And not just like expose every function to the user and say like, oh, well, like you just figure out how to use this, like whatever. You know, we need to like really help these people out, because that's our job as experts, to not just sort of say like, hey, you know, just like throw them in the deep end and hope that they don't drown.
Well, thank you so much for sharing all of this with us, Ben.
Yeah, thanks for having me.
And to our listeners, thanks for listening.
Thanks for listening.